Today we're going to show that every integer greater than 1 is divisible by a prime number. It's not an earth-shaking fact. We're just going to prove it as a way of practicing strong induction. Okay, so let me write down what it is that we're going to prove. Every integer greater than 1 is divisible by a prime. Okay, so it would be a good idea for you to take a minute and review the definition of prime and composite, which are definition 4.5 on page 116. Okay, that would be a very good idea because we're going to use those definitions. Particularly, you need to know the definition of composite. All right? Okay, so let's prove that. Okay, let's just give us a symbol for the set of integers greater than 1. Okay, now we're going to do this by strong induction. All right, so let's do this like we always do. Let S equal the set of n in A such that n is divisible by a prime. Okay, or just so that you can see different ways of writing that, I could have written it like this. S is the set of n in A such that P divides n for some prime P. Okay, our goal is to show that S is all of A. Okay? All right, so let's do our base case. What's the first number in A? First number in A is 2, right? So we want to show that 2 is divisible by a prime number. Well, that's easy because 2 is prime, right? And 2 is divisible by 2. So therefore, 2 is divisible by a prime. That's pretty straightforward. Notice that 2 divides 2. Okay, if you really want me to be pedantic, let's point out why that's true. Since 2 equals 2 times 1. Okay? And also 2 is prime. Hence, 2 is divisible by a prime, and so therefore it's going to be in the set S. Okay? I'm not proving here that 2 is prime. I guess we could have, we could do a sub-proof inside of this proof, proving that 2 is prime. But that's not what I'm trying to prove. I'm not trying to prove that 2 is prime, and so I'm taking that as a given fact that the reader knows. Okay? Certainly, if this reader is trying to prove that every integer greater than 1 is divisible by a prime number, then I think it's reasonable to say, okay, so this reader must know what a prime number is, and if they know anything about prime numbers, then they know that 2 is one of them. Okay, so I'm not proving that 2 is prime. I am taking that as given knowledge. Okay? What it is that I'm trying to prove is about divisibility by primes. I'm not trying to prove which numbers are prime and which ones aren't. I'm trying to prove that certain numbers are divisible by primes. So I did take the effort to show that 2 is divisible by a prime. That's what I showed in this line up here. Okay? All right. So that's our base case. Now we're going to do our inductive hypothesis, and we're going to use strong induction. Okay? And let me point out a minute why we're going to use strong induction. If I wanted to use regular induction, then I would say this. I would say that if a integer greater than 1, let's call it n, if n is divisible by a prime, then I would like to use that to show that n plus 1 is divisible by a prime. Okay, that's probably not going to be very doable if you think about it, because we're talking about divisibility here, so we're talking about factors. The factors of n plus 1 are very, very different than the factors of n. So just because n is divisible by a prime, in other words, I could say, just because one of the factors of n is prime, how is that going to help me show that the factors of n plus 1 has a prime in them? Probably not very doable. Okay? So what I'm trying to say is that in order to show that n plus 1 is divisible by a prime, I'm probably going to have to look back at more numbers than just the previous number. Okay? All right, so that's why I think we're going to need to do strong induction. So let's write down our inductive hypothesis. And just so that you can see different ways of writing the inductive hypothesis, I'm going to write it this way. Suppose that for any k in A with k equal to or less than n, we have k is an element of S. So that's just one way of saying 1 is in S, not 1, because A starts with the number 2. So this is a way of saying 2 is in S, 3 is in S, 4 is in S, 5 is in S, all the way up to the number n is in S. That's our assumption. The numbers 1 through n are all in the set S. I want to use that to show that n plus 1 must be in the set S. Okay? So let me go ahead and write here. Now consider n plus 1. Okay? If, I think we can agree that n plus 1 is either a prime or it's not, right? So if n plus 1 is prime, then n plus 1 is in S, since n plus 1 divides itself. I'm going to say n plus 1 equals n plus 1 times 1. This is just like we did with the number 2. Okay? I can even add on here if I feel like that's not enough. I can even say, and hence n plus 1 divides n plus 1. Okay? So if n plus 1 is prime, then it's in S. What's the other possibility? The other possibility is n plus 1 not being prime. If, on the other hand, so I'm really doing a proof by cases here. If, on the other hand, n plus 1 is composite, now this, I still need to finish that sentence, but I'm going to stop for a second. Do you see that we're really doing a proof by cases right here? Case 1 is n plus 1 is prime. Case 2 is n plus 1 is composite. Okay? All right. If n plus 1 is composite, then, so again, you might want to look at the definition of composite on page 116. Okay? What does it say? If it's composite, then it can be written as A times B for some integers A and B where A and B. So, okay, this is how it's written in the book. It's written like this. I don't like this, and I'll tell you why. That they're trying to say A and B are both between 1 and n. I don't like it writing that way. It's very ambiguous. That might be saying A is greater than 1 and B is less than n. Okay, I don't think that's a very careful way of writing it. I think it's better to do this. Okay? All right, now let's look at that number A. Or I could look at B, but I just need to use one of those. I'm going to use A. Okay? Since A is an integer and one quick mistake that let me fix here in this previous line. We're talking about n plus 1, not n. So over here, those should both be less than n plus 1. Okay, sorry about that. All right, let's continue. Okay, since a is an integer and a is, I can tell you this, it's at least 2, right? Since it's bigger than 1, then it has to be at least 2. Because it's an integer and it's bigger than 1. Also, because a is an integer and it's less than n plus 1, then that means it's less than or equal to n. Then what can I say about a? Let me give you a hint. It's right here. You see, look, let me point this out. Here I've pointed out that a is an integer. And here I've pointed out that it is equal to or greater than 2. Those two things together tell us that a is in the set capital A. All right? And then furthermore here, the fact that a is less than or equal to n allows us to say by our inductive hypothesis, that allows us to say that a is in the set S. Do you see that? So, because a is an integer and a is at least 2 and less than n, then a is in S. What if you're afraid someone's reading this and they're not going to understand why? Why is a in S? Okay, then we can say by hypothesis, and then that tells the person, if you're confused why this is true, just look back at the inductive hypothesis and you will see why. Okay? All right. If a is in S, then what's that mean? That means that a is divisible by a prime number. So hence, P divides A for some prime P. Okay. What does that mean, P divides A? It means that A equals P times an integer. So let's write that out. In other words, A equals P times some integer. Let's call it M. We're running out of letters. So can't use N, can't use K, so let's use M. Okay, for some integer M. But that means that n plus 1, which we've already said equals AB, can now be written as PM times B, which by the associative property is the same as P times MB. And because M and B are both integers, then MB is an integer. So I have n plus 1 equals P times an integer. So P divides n plus 1. and therefore n plus 1 is in the set S. Which means by the principle of strong induction, S equals A. And that's the end of our proof. Let's see if we can look at it all at once. Hopefully that's still big enough for you to read. Okay, not terribly long, a little bit longer than the others, but not bad. It's a proof by strong induction, and it's also a proof by cases, because we had the case in the inductive step. The case is n plus 1 is prime, or n plus 1 is composite. Okay, so nice little example. Not terribly long lecture today. Good to get practice though. Have a good weekend.